Welcome to this session on cloud design patterns. In today's session, we'll be talking about 35 to 40 minutes. So I would like you all to make a guess on the number of design patterns that we are going to talk about. Let's see. If the number is right, then it's 4. Okay, that's not the right order of the design patterns that we will talk about. So I know those are the design patterns, but another guess would be guess the order of the design patterns that we'll talk about. Well, some of you guys may be interested in guessing. I have a personal story to share. So me and design patterns go way back. Back in the days, when I was still learning my first set of design patterns, I think it was singular and abstract factory patterns. I was given a coding assignment, and I worked on it, and time comes for the code review. Drum roll again. Because I've applied a lot of design patterns. I've tried to apply the design patterns everywhere that I could fit it in. And back in the day, my software guru, he was a man of very few words. He called me in, and he just showed me one simple picture, and he didn't have to explain anything else. And it was very similar to the next slide that I'm going to show you guys and girls. That's the one. It's not very similar to the spore cat that's getting abused, but it tried to fit in a wrong place, and that's what happened. And when I was planning on design patterns, it reminded me of those days. Anyways, let's get back to this first caching pattern. In cloud, there are two types of caching. One is in-memory cache, and the other one would be shared cache. In the in-memory cache, the data is stored local to the computer that your application instance is running on. Let's say you have application instance 1 and application instance 2. Both of those will have its own set of cache, and they will have their own copies of data. So typically, you would use in-memory caching for some static data, or more interestingly, some local computations which are like complex and you don't want to recalculate every time. Then you could store those kind of computations in the cache. Let's get to the more interesting cache service, which is a shared caching service. If your organization is able to afford a out-of-the-box solution, then you don't have to worry much here. You just have to know the concept and leave for this specific pattern and come back after the break, of course. But if you want to implement something, then I want to introduce a concept called read-through and write-through caching. It's not invented by me. When I say introduce, I definitely don't mean that I invented it. But again, I'm trying to introduce the concept itself. So in read-through caching, what read-through caching says is you just load data on demand. So when a request for an object comes to the cache and to your cache service in this specific case, then you check if it already exists in the existing cache. If not, you go to the database and fetch it. It could be SQL or NoSQL, n number of databases, it doesn't matter. And then store a copy of that object in your cache. And the more interesting part is how do you invalidate the cache using a write-through mechanism. So if some change has happened, then how do you invalidate the cache? I can think of three solutions. One is you just invalidate the cache when an update request comes through your cache service and make a call to the database and update the data. Done, right? And when the read-through caching kicks in, it'll go fetch the latest version of the data because it's only on demand. Okay? The next option would be make two asynchronous calls, one to the database and one to update the cache. In both of which scenarios, um, we need to make sure that that's a transaction that's happening. Otherwise, you will end up with inconsistent copies. The third option, and more interesting option, is right behind operation, where you keep updating the cache, but you don't update the database just when the object that you have is about to be booted out from the cache. Booted out in the sense kicked out from the cache because of either the cache expiration or some other policies that you have for the cache to expire. You just kick it out and update your changes to the database. So when you're updating your cache, typically you are stuck with two options. If you're not invalidating the write-through caching, which is concurrency. How do I handle the concurrency? I always make sure there are two approaches. Typically, most people use the more optimistic approach, but there are cases where your data is too sensitive, and if it's not that well designed, sometimes you may end up with a pessimistic approach where just before you update, you verify the timestamp. If the timestamp doesn't match when you have retrieved it, then you'll have to resend the data and say, hey, the data has changed. Do you want to still update? And then make a choice at that point in time. Okay? With the read-through, I think I have cut through the next pattern, which is our cache-aside pattern that I wanted to talk about. So essentially, when using read-through caching, which needs to implement a cache-aside pattern, then you would want to implement a write-through caching solution. Okay? So essentially, all cache-aside pattern is, if the item is currently not held in the cache that is being requested, you get it from the data store and store a copy of the item in the cache. As simple as that. Okay? Applause, please. We completed our first pattern, and let's go ahead and see some concepts before we move on to the next three design patterns. Okay? So the concept that I wanted to talk was eventual consistency. So I want to differentiate between strong consistency and eventual consistency. So in cloud, we have to have eventual consistency, because the bad news is, if it's strong consistency, all the changes need to be atomic, and holding a long-running transaction across a geographically distributed database is seemingly becoming impossible to achieve, because a simple network failure could just hang the transaction up and the system is not in a usable state. Whereas in eventual consistency system, all the work performed by the transactions will be either committed or rolled back at some point in time, maybe not this very specific instance, but it has to be consistent at whenever they are able to complete, it will be consistent. Okay? The promise that an eventually consistent system makes is no updates are ever lost. So going back to history a little bit, eventual consistency stems from something called CAP theorem, which states that the distributed databases or distributed systems are subject to CAP theorem, and at any given point in time, only two of the three features, which is consistency, availability, and high partition tolerance, only two of the three elements can be not elements, but two of the three properties will be achievable. Okay. Some people also call this state as base state, which is basically available, but in a soft state, which means it's still fluid and there are transactions happening at this point. Okay. So let's go ahead and, enough of the theory, right? Let's go ahead and see what are the steps that are required for achieving eventual consistency. Let's consider this order management system, which involves code creation. So when you order something, there is a code created, and once the quote is approved in my specific order management system, once the quote is approved, then it goes back to the order management system, and it determines if the orders need to be created, and if the orders are created, then how would I generate invoices? It's all the business process which we could care less. But think of some system as a workflow with a bunch of steps. Okay, so if you have a workflow, then the steps within a workflow need to be made idempotent. Okay, what do I mean by idempotent? When I say the term, then the steps, the same step that has been run before, we should be able to run the same step again, and it shouldn't change the state of the system. Let me repeat that. When I run a certain step within a workflow, I should be able to come back and run it again without changing the state of the original system. Okay? Once your steps are idempotent, then you should be able to rerun any of the failing steps multiple times. Of course, we'll have a certain limit on the retry, and if the retry options run out, then you obviously realize that, oh, I'm not going to be able to run through this transaction, so I have to roll it back. So you should be able to have some kind of compensating logic. And more interestingly, when you're updating stuff, it is a key detriment if two instances of the system are trying to update the same record. So for that, you need to partition the data in such a way that maybe you split the record into two different tables or two different data sets, however you want to deal with it. So you partition your data so that two instances of the same system are not trying to update the same record at the very same instance of the time. Think of two departments trying to access the code and updating the code record. Instead, if you split it appropriately for the two departments, then it would probably avoid that situation. And of course, for eventual consistency, the system has to be event-based system, where your system is reacting to the commands, and the events are generated, and you react to the events and process them. Okay, these are the 5 steps. Okay, let me repeat them. Idempotency, retrying failing steps, partition your data to avoid concurrency issues, make your system events-based, and of course, when you cannot go through a transaction, you'll have to roll it back, so you need to have compensating logic in place. Okay? I don't want to bore you guys with the domain-driven concepts right now, but I have to explain one key concept called aggregate. So when you have a bunch of objects, like a set of related objects, where your transaction scope is defined, then you consider that as a consistency boundary, and you treat those set of objects as a single unit, as a logical single unit for the purposes of just the data changes. They are not interdependent, but when changes to a certain object obviously automatically implies changes to some related object, not necessarily through any foreign keys or anything like that. But if there are like related objects that could be affected by a certain transaction, you consider those entities as an aggregate. So the technical definition, more of a technical definition for an aggregate, is it's a cluster of related objects that are treated as a single unit for the purposes of data changes only. Okay? And of course, aggregate root is like a root entity where you can access all these related aggregate objects. Okay? And that's all you have to know about for this specific session. Let's quickly wrap up by having these commands and events. So what is a command? It's like a request for the system to perform a specific action. Okay? Whenever an end user makes some changes or wants to view some data in the user interface, it's a command. And what is an event? Events are nothing but notifications. They report something that has already occurred in the past. And if you are an interested party for listening to the event, then you either react to it or you say, okay, there is nothing in this specific event that I need to do. It could be like a duplicate. Okay. Another important process in this achieving eventual consistency or in making the steps idempotent would be deduping logic, where you identify a duplicate message and don't do anything about it. That's called deduping. I think every system has one. Like in my systems, we have customer deduping or invoice deduping. If it's already paid for a certain period of time, we don't make those invoice payments again. Okay, something like that. Or if you check if the customer already exists with the given information, then you don't create a new customer. That's called deduping. Okay? So these are the key concepts in achieving an eventually consistent system. So let's see what are some of the patterns that would be required in helping us achieve that. So let's go backwards and talk about the compensating transactions pattern real quick. All right, let's check here. Okay, so this this occurred back in the way back when I was ready to take one of my first flu shots. Flu shot is like an injection that they stick inside you, and I did not realize that I was developing a fear for needles over the time. So I went to the pharmacy and gave them my insurance, and they said, okay, we need to process some stuff. Just come back after a few minutes. So I did as I was told, and when it was time to take the needle, I was like this dude over here, not specifically want to point to a specific person, but I was like freaking out. There's no way I was going to take that needle. I said, okay, I chicken out. I don't want it. Then she said, oh, no. We processed your insurance. We checked out the stock, and we even notified some health agencies that were interested in getting notified. Then I said, oh, man, I wish there was like some kind of pattern that would roll this entire list of steps she was reading to me. And this was like these are like very few steps that I'm giving out, but probably they have a little bit more complex logic. Anyways, so I felt, and when I read about this pattern, I was like, aha, this was like the perfect solution. So whenever you have a workflow and a step is performing an action, you have to, if required, to roll back, you'll have to write the corresponding information that you would need in case of a rollback. Like in this case, when you're notifying the insurance, you speak with an identifier, and when you have to cancel that, you speak back in the terms of the same identifier. Similarly, for checkout, you should have a logical ID, and whatever identification that is required, you'll have to store it somewhere. And when people like me chicken out, then all you do is implement some compensating logic. So the reason I'm mentioning compensating logic instead of just calling back the identifier with cancellation is the state of the system could have changed. So when the identifier was created for the insurance company to process my flu shot notification, then at that point, it was probably in the unpaid state. But by the time I chicken out, probably the insurance company has already paid the pharmacy. So your compensating logic needs to verify that it's not, if it has already been paid, then you need to refund that payment to the insurance company because I did not take any flu shot, and act appropriately on your existing system. So that's what I mean by compensating logic. So all these things apply best in case of workflows where you have a appropriate workflow for all the for your specific domain. Okay, so if that was the case, then I would have been a very relieved person. I felt this was a funny analogy, and when I read this pattern, then maybe I knew all about this all along, and I just did not know the right terms. Maybe it could occur to you too, right? There are situations where you want something to be rolled back, and anyway, so let's move on with something called event sourcing pattern. So what is event sourcing? Event sourcing is a pattern that tells us how to save our entities by just appending our existing events that are happening to an existing transaction log instead of updating this existing record that you have. So on the left hand side, if it was still an command handler that you're listening to and reacting to, then it would talk to an ORM layer, which is an object mapping layer, and that would update a record in your database. And when you query for it, you read back the results, and that's the end of the story. But in this specific case, you would keep adding. Let's say it was like a request to make reservation for seats, and you don't have to display it publicly how many seats are available or anything. Then in that specific case, you could just keep appending those requests to an existing transaction log, and whenever you want to make a reservation, you make sure that the seats are appropriately available using an aggregate that you have. So what does this pattern really help me with? So if I have to view the UI, all I do is I replay the list of transactional events that I have and get to a specific state. But what are the considerations that I have? Obviously, the reads are going to be slow. There's no given to that. But there is a solution for that, which is called snapshot solution. There could be multiple solutions, but the solution that I heard and know of is snapshotting. So when you write to those events, so let's say every 100 events, you sum up those events, you summarize those events and store it as a snapshot so that going forward, you bring the latest snapshot from the database and just replay those other events. So it will all make more sense when I go to the next pattern, which is command and query segregation principle, where your read side and write side are separate databases for that specific domain piece of your application. Other than that, what are the considerations other than the slowness that I have, which is probably the versioning of the events. So you may store a little bit more information or delete some existing information. So when you're building your aggregates, you need to be careful in designing those things because the events may change over the time, but you still should be able to replay those list of events and get back to the view state that you want. Okay? But what does it give me as a benefit? It gives me faster updates, less concurrency problems. Because what is an update technically? It's just an delete followed by an insert. That's two operations. But in this case, you're not doing the delete, you're just inserting, which will make it much faster. And the second thing is when you're updating, you don't log the record. There is no concurrency problem. So you just keep appending to the transaction log. And when you want to get to a specific state, you replay the list of events that have occurred so far and get to a certain point. There is some concurrency that you will still have to handle, but it's not as bad as locking a specific record. Okay. Again, there are scenarios which are appropriate for this. Not every CRUD operation can be replaced by a events-based system. Like I said, there is a time and place for everything in design patterns. Okay. I only gave you these two major advantages, updates and less concurrency locking, but there is a whole bunch of advantages of using event sourcing. The first, obviously, the very first thing uh, that it gives away is the audit trail. You don't have to maintain any audit trail. Your event log is pretty much the audit trail that you have. You can derive patterns using your business intelligence solutions if you have entities, because a list of entities can be projected into any structural representation that you want, or you can derive more patterns from it. It makes your production troubleshooting easy because you can see the entire audit trail. And this one was more interesting to me when I was first learning this pattern, which is fixing errors. Because there are times in everybody's life where there is a release that has occurred, and the very next morning you realize that there was a blunder that you made, blunder in the sense a bad mistake that you made, and you want to roll back, you want to fix it and apply the patch as quickly as possible. But in that case, if you implemented this event sourcing pattern where you have this list of all these events appended, all you have to do is to get to the right structural representation, you invalidate the snapshots that we talked about, and you start replaying this entire list of events to get back to the correct state. So in that way, it's easy to fix some errors. Of course, there is no given um, on how easy it makes the testing, and I think we already talked about the flexibility. Okay, so that's event sourcing for you in simple terms. So let's talk about the very last principle, which is command and query segregation principle. So what does command and query segregation help us? In place of one single object for each entity, now it's saying just create two objects. One is for the read and one is for the write. Sounds very complex. Ooh. No, it's not really that complex. It's funny that I say that, but of course it adds complexity. I said it in a funny way, but there is no taking it away. But the more interesting aspect is the beauty of this pattern is it helps you with the read side and the write side, where you can optimize each of your databases independently. So when you're optimizing your read side of the objects, you make it more write optimized. When you're designing the write side of your operation, you make it more write optimized. But when at the same time, when you're reading from your read data store, you can apply the materialized view pattern where you have materialized views you can read from, and it can be more geographically distributed. There are a lot of techniques where you can distribute your databases appropriately. But again, the read store, all it is a bunch of events that are acted upon on a certain, it's like an audit trail that you have on a specific database. Some people, very simplified version would be having a master slave architecture for your databases, where your slave databases are pretty much your read side databases, and your write side is obviously the master database, which has to again send out the operations that are performed on it to the right side of the things. Okay. So what are the considerations that I need to look for when implementing this specific pattern? So the obvious benefit that we talked about is it separates the read side and the write side. And for the right side of it, you can use the more senior developers to work on the right optimization, which is a more challenging task and requires some domain knowledge. And for the read side, it's a nice way to welcome new developers by giving them the more easier tasks and getting them accustomed to the domain, and give them more flexibility and less chance to error. And you're helping them succeed in a better way. And you should only use this pattern where your systems can only be eventually consistent. because there is this read side that needs to be synchronized to the there is this write side that needs to be synchronized to the read side. So obviously there is some lag, which means it can only be an eventually consistent system. And of course, it can have multiple operations that are performed in parallel, which can be eventually transmitted to the read side. Okay, and only applied to the, because of the complexity or overhead of two objects that we need to have, try to apply to the parts that are appropriate and needs good load balancing and stuff like that. Okay, and that's all I have on the design patterns of it. So if anybody is interested, I can talk about some best practices from the cloud. I can hang out for a few more minutes and let's talk about some good cloud practices. So one of the key benefits of cloud is elasticity. So what is elasticity? So it is the ability to scale your resources up or down depending on the demand that you have for your system. So that being said, what are the steps that would help me as a developer that I can take, or a manager that I can take to achieve elasticity? The first step would be make your systems more repeatable, make your deployment process more repeatable. That means you need to have automated deployments or a very systematic thing where there is very less manual intervention, and you should be able to install the software any number of times on any number of machines. Okay, that's the first step in achieving this elasticity. And the second thing that you need to do is write your code by not fearing constraints. When I say that, it can be a little confusing, but when I explain it, it'll be more clear. Okay, there are things that I talk are there are concepts that I talk are confusing, but I can explain them. Okay, no big deal, right? So you need to write your code by not fearing constraints, which means that you could receive any amount of RAM on your machine, on your server that you are going to get, on your VM that you are going to get. But if your system is capable of implementing caching, which is like a shared cache service, which could have any amount of data, then you shouldn't have to be worried about how much RAM I'm going to get on this specific machine. If you are depending on the if you are dependent on the cache, then obviously your computations and all those things don't have to be performed as many number of times, because those computations can be stored locally. You don't have to re-repeat. You could have snapshots of your computations, just like we had snapshots of the event processing aggregates. Okay, so that's what I mean by not fearing constraints. When you move to cloud, you cannot always guarantee what kind of system configuration you're going to always get. But if you write your code in such a way where it's not dependent on a specific hardware part of it, then you are better off and easy to make it more elastic. Okay. The third thing is virtual administration. This is like a more like a hint rather than a specific behavior, where you will have to train your network administrators or the people, the IT, your IT folks, to be more of a virtual administrators rather than the more like how to use the automated deployment processes and stuff like that. Okay, so that's what these are the kind of steps that help you move towards elasticity. So let me repeat that again. An automated deployment process or a very repeatable processes for your deployments. Write your code where you don't have to worry about the resources that you are going to get, amount of resources that you are going to get. Use what you need to be. There is a lot of training involved where the administrators need to be trained to run the scripts to scale up or down by monitoring them. Okay, these are the steps that are required for elasticity. So let's talk about designing for failure. So take a very pessimistic approach when you're designing your projects or softwares or hardware for that matter. So let's talk about a hardware failure scenario that could happen. So when you're having a master slave architecture where you have a master database which takes in all the updates and replicates to its corresponding slave databases. Let's say if the master database fails, you need to have an algorithm in place which will determine which of the slaves is going to become the new master. Okay, that's one of the ways to handle the hardware failures. And for software failures, let me think through an example where I could have a software failure. Let's say I'm talking to a third-party payment system, and they decided, okay, I'm going to change my interface. In which case, uh, you'll have to handle that gracefully. So if the interface has changed, then you would have to cut out the payment system and say we are not able to process your payments at this point, or um, how do I? There are times where I am more dependent on the WSDL. So in that case, you could have a dynamically generated WSDL. There are different ways that you can call a web service. You could have the WSDL hard-coded, or there are cases where you can flip back and get your WSDL dynamically by pointing to a URL, and you can make a SOAP request that way. Okay. And the third thing is, of course, asynchronous architectures. Everyone knows these days, like everything is asynchronous call. So if you decouple your components, which helps you drive towards asynchronous architectures. And of course, think parallel. There is a lot of parallel processing when you're designing your workflow steps. See if you can make parts of those workflows. Of course, not everything can be parallel, but wherever it's possible, try to make it parallel. Keeping the dynamic data closer and static data closer to the, of course, keep the dynamic data closer to the compute solutions, like your servers, and static data closer to the end user. Like, let's say if there is like CSS or a bunch of JavaScript files, then you would want to use the content delivery networks, which are much closer to the user. And of course, when you're computing something, then anything that is more changing, then you would want that to be closer to your servers. Okay. And now I'm going to play back the original slide. That's all, folks, for now. Okay. Thank you for attending this session, and I hope you all had some good time.